Remember on the previous page how hard it was to make it all the way around the circle in faster than 1 second. That is because mouse clicking is just slow. Now we will let the browser do the clicking and you choose how fast you want to go, from 0.1 Hz up to 2 Hz. Anything above 2 Hz just looks like flashing and it's hard to see what's going on. There's a lot happening on this page, so let's break it down. On page 3, we plotted sine of theta. On page 4, we plotted sine of 2 pi times frequency times time. Here we will show that the page 3 theta can become 2 pi times frequency times time, when we will click all the way around the unit circle in increasing phase. Bringing frequency into theta allows the curve to change when we go around the circle faster or slower. Let's look at the equation in the top left corner. The angle theta, which is bold black and in top middle, is two things. First, it is the angle we see in the unit circle where each dot represents 30 degrees or pi over 6 radians, or alternatively 2 pi over 12 radians. Remember, theta gains 2 pi every time it completes a revolution, so we need to keep track of that. We keep track of this for you under the section observed values. N is the number of times it goes around the circle and is in red, and theta sub u is the leftover part of the angle and is shown on the unit circle again in green. Adding these two together gives the observed value of theta. Let's hit the start button at the lowest possible frequency of 0.1 Hz and watch what is going on. The box section in the middle keeps track of values for you. For now, let's just look at the observed values of theta on the left as they increase. You can see the unit circle values are the same as the green values in the box, which is the same as inserted into the equation above the box. Now notice I keep the values of theta sub u in terms of 2 pi, so that when I factor it out below the box, it's easy to see where the numbers come from. Notice that every time we make it back to 0, completing a cycle, we increment n and theta gains another 2 pi. Stare at this as long as you like, hit pause as you like to verify the values, and hit clear if you want to start over from 0. In the next segment, we will look in detail at the right side of the equation and pull this all together. Okay, so now we understand how to observe the values of theta. Let's look at the right side of the equation under the header, given values, and see how to predict these values. I have reset the page so it's back to the default values. Frequency is the slider you adjust from 0.1 Hz up to 2 Hz. The resultant value in magenta is saved in the box of values and inserted into the equation above the box. Time is in purple and it starts at 0 when you first enter the page and starts counting up in real time when you click start. And you can verify this with your phone timer if you like. It pauses when you click pause and picks up where you left off when you click start again, and you can start time over again by clicking clear. I'm going to go ahead and click start. What are we doing here on the second line is multiplying the frequency times time. Then, to make it easy to compare to the previously discussed observed value on the third line of the equation, which is below the box, we pull out the integer part of the value and express the fractional part as a value over 12. Let's hit pause and verify the calculation. You might get slightly different values than I do depending on when the pause executes relative to the time increment, but it will be close and you can verify yourself with your actual numbers. I get, for a frequency of 0.1 and a time of 25 seconds, a value of frequency times time of 2.5. Pulling out the integer part of 2, I get a fractional part of 1/2. Multiplying the fractional part by 12, I can express the fractional part as 6 over 12. Thus, I can express the frequency multiplied by time as 2 plus 6 over 12. Hey, wow, this matches the observed theta values I see over on the left. You can restart the timers and pause again and check the calculated values on the right and compare to the observed values on the left. Now that we understand why theta equals 2 pi times frequency times time, let's move on to the next segment of this demo and go faster. Let's look again at the trig functions for frequency of 0.1 Hz. The period for this waveform is 1 over 0.1 Hz or 10 seconds, and this is shown by the purple circle on the upper right graph. Now let's increase the frequency to 0.5 Hz. The upper plot shows 5 revolutions around the unit circle within 10 seconds. The lower plot more clearly shows the period of this waveform for 2 seconds. As we increase the frequency, the period of repetition decreases and we get more cycles in the time frame. Isn't this more interesting than the original plots we saw on page 3, where you got the same curve whether you went around the circle fast or slow? We'll take it up to 1.5 Hz. The upper right plot had to drop some sample points to keep the graph readable. The period of 1 over 1.5 or 0.7 is seen clearly on the lower right graph. Play around with this as much as you want, hitting pause to verify the numbers, clear to start over, etc. I wouldn't let time grow too large, else the table will get distorted, but you can hit clear to fix that. At 2 Hz, we are still below the range of human hearing. On the next page, we will not show the samples being collected, which will allow us to work with frequencies in the audible range.